So any other questions? Okay. Yeah, so I will now go back. So what were we doing actually? So we have defined Fourier, and I mean, so we have seen that on a finite abelian group, we have a full basis of characters for the L2 of the group, and we have seen the Plancherel relation. And last time we also saw that Fourier inversion formula, because we saw that G hat has a group structure in by pointwise multiplication of characters. Characters are functions, so you can multiply them pointwise, and that makes it a group. And G double hat is actually isomorphic to G in a natural way. The evaluations. So if you where is the okay, where is that evaluation? So if you look at chi of x, chi is a character and x is an element. If you look at it as a function of x, it's a homomorphism of G. But if you fix x and look at it as a function of chi, then it's a homomorphism of G hat. And these are all the homomorphisms of G hat. That says that each x in G gives a character of G hat. So G double hat can be identified with G, and consequently that led us to, sorry, there is a little bit of this. I hope it's, yeah. So there is a, this gives a duality, and G double hat can be identified with G, and we also have the Fourier inversion formula. F hat, hat is actually F hat will give us F of F flipped over. F hat check will give us F. So that's the Fourier inversion formula. Okay, and that's what I did last time. Okay, so then I will proceed to one more general property. I mean, it's a called Poisson summation formula. Okay. At the moment, I don't have applications for this Poisson summation formula. I mean, the continuous Poisson summation formula, there will be many. But for the discrete one, I have to look up actually. So this one, what I'm going to say is kind of, yeah, I have to look up what is a good application for this one. But it's very analogous, and even if I can't find anything direct use for this, what we will see is that this will give an analogy. I mean, later you can see the continuous Poisson summation formula in analogy with this. Okay? So that's what we will do. So now let's see. So G is a finite abelian group. And then we have G hat is the so by the way, we call G hat the dual. Because after the duality relation, it makes more sense to call it the dual. Dual is always something that if you take the dual of the dual, you should, I mean, it's a, you should get back the original. That's what duality usually means. So G hat is called the dual group. It is the collection of characters of G. Now, what I want to do is, suppose H is a subgroup of G. I don't know how it's written, something like this. And G mod H is the quotient. Okay, sorry that I will not be able to explain all this. I mean, I will assume you know this. If you don't know this, you can skip the entire Poisson summation formula for now and look it up later. Okay. So since we are working in abelian group, every subgroup is a normal subgroup. So G mod H is a quotient group. Actually, it's a group also, and we have a map, quotient map from G to G mod H. So let's call it Q. It's the quotient map. Okay, so this is the quotient map, and now suppose I have a character here. So this is a character not on the group G, but on this quotient group G mod H. Okay. So then, of course, quotient map is a homomorphism. So composition will be a homomorphism. So if I take this, chi compose Q is a character of G. Okay, so I have G to G mod X is the quotient map. G mod X to the circle group, I have a homomorphism. Then the composition will be a homomorphism from G to the group, G to the circle group. So this is circle. Now, what I want to do here in Poisson summation is this. So I have a function f in L2 of the group. Okay, so let's start with a function in the L2 of the group, the larger group G. I want to make a function on G mod H. Okay, so we build. How do I define a group on G mod H? Okay, so G is broken into cosets by this. So this is the whole group. And here are the cosets. One of them is H itself. And if you want, they will look like translates. All the cosets will be basically for those who haven't seen algebra in a while. So what coset does is there is a subgroup H. Then you can write the entire group as a union, disjoint union of translates of H. And so on. So in this case, everything is finite. So the whole group can be partitioned into the subgroup and some of its translates. Okay. So each of these is called a coset. So these are called cosets of H. Each of this is a coset. It's a subset of G. All of them being translates, they will have exactly the same size, of course. Okay, so now what I want to do is, so G mod H is basically thinking of each of these as one element. Okay, so this is one element, this is one element, this is one element. That collection of cosets, that is G mod H. So what I want is a function. I want to build a function on the coset, function on the quotient group, which means if you want, you can think of it as I want to build a function on the group which is constant on these cosets. How do I do that? Okay. F how do I build that? So why? So you take all the translates of it. That's it. This is capital. So you take any x in the group. It's so let's say x is any. It can be anywhere. So you take. Oh, sorry. What did I do? Its translates would be its translates is basically all these elements actually. If you translate by h, these are all the elements which differ from x by a element of h. So basically I'm taking the sum of capital F over this set. That will be, so if you call this, give this cosets name C0, C1, C2, etc. I am defining a function, or rather, sorry, why do I write x here? Sorry, okay, I just watched the notation, so let me say it again. So let's write f of a coset. The coset is one of these sets. So let's say f of c will be just sum the capital F over this entire set. Over x in that coset, or if you want x in q inverse of c. All those x whose q will give me this coset, okay, C1. This is basically all the elements here. So this is how I define. So this becomes, so then, of course, this is well defined. This is a function on G mod H, and then F is in L2 of G mod H. Okay. So what is this? Okay. For since although I have not introduced continuous Fourier transform, but I think that many of you are to a greater or lesser extent familiar with it. So let me just explain what is going on here. It is a kind of thing that is often done in both mathematics and in electrical engineering. This is something that people do all the time. Suppose you have a function on R. So continuous Fourier transform considers signals on real line. But you also consider periodic signals, that is Fourier transform on the circle. Okay, so how to build So if I define f of x to be if I sum it, okay, for this to be meaningful, this capital F better decay fast at infinity so that this infinite sum makes sense. So assume convergence and all. Which is okay if F is in L1 of R. If it is integrable, then it is fine. But don't worry about that. Think of a function with a fast decay like a Gaussian. You can make a periodic function out of it by summing over all the translates of it. So then this becomes a 2 pi periodic function. So that's exactly the analogy what we are doing here. Okay. So we want a function. So here R is a group and Z is a subgroup and R mod Z is isomorphic to the circle group. Okay. So from a function on R, I build a function on R mod Z, which is the basically function on R mod Z, a function on circle, same as 2 pi periodic function or function on the circle group. So this is how you build a 2 pi periodic function from a function on the real line. So what I'm doing here is exact analogy with that. Okay. So I'm summing over. So what is it I want? I sum over all the things which differ from it by multiples of 2 pi. Here I am summing over all the other points which differ, so to speak, from x by an element of x. That's what we are doing. Okay. I hope that makes it a bit more clear if it was not clear earlier. So the question that I want to ask is, so now we have this. So on the one hand, a function on L2 of G from which we have built a small f which is on L2 of G mod H. On the other hand, here we have a character on G mod H and from which we have built a character on G. So the question that I want to ask is, relate f hat of chi with capital F hat of chi compose Q. Okay, so small f is a function on G mod H, so we can take its Fourier coefficient at a character of that group. Capital F is a function on G, we can take its Fourier coefficient at a character of that group. So I want to relate this with this, and that will be the Poisson summation formula. Okay, it's just we just follow the definitions; it will follow. Nothing complicated is going to be here. So we just calculate f hat of chi compose Q by definition is 1 by square root n f inner product chi compose Q. This is the definition, right? Which is n is the size of the group, big group. So it is 1 by square root n sum over x in G f of x chi of Q of x conjugate. Now let's sum this by fixing the cosets. I have to sum over all group elements, but let me sum it over cosets and then each coset and then sum it over add all those. So how do I sum it? Since the group can be partitioned in cosets, so I will sum over for each coset of G by H. I will just sum over all those x which belong to that coset, which is x is in Q inverse of C. That means those x for which Q of x is C, that is x in that coset of the same quantity f of x chi of Q of x. But chi of Q of x, let's just write this. But by definition, Q of x is C, right? So that comes out and I get so this is chi of C bar. So I get and then sum over x in q inverse of c f of x. But what is that? By definition, that is my small f. Okay, so that is just f of small c. By definition, f of small c is just the sum of capital F over the coset. So this is f of c chi of c bar. But what is this? I mean, so okay, so let's give some name. M is the size of h, suppose. So then I should have divided by square root of m to get f hat. So I'll just write this as square root m over square root n into f hat of h. So this is the relationship between the, okay, this is not Poisson summation. I'll write Poisson summation. So this is the relationship between the Fourier transform of capital F and the Fourier transform of small f. So, yeah, question?
Can you repeat the reasoning of the third line there? I didn't fully follow.
This one? Yeah.
Yeah. Yes.
Okay. So let me actually just go over the whole thing. So capital F, we want to take the Fourier transform at the composition character. So we start with the character of G. So see that we go in the other way in the two things. The function, we start with a function on G and build a function on G mod H by summing over the coset. Character is the other way. We start with a character of G mod H and build a character of G by composition with the quotient. Now I want the capital F Fourier coefficient at chi compose Q. So I just follow the definition. It is 1 by root n. N is the size of the group. F of x chi of Q of x conjugate, which I break into cosets. Okay, so summing over cosets. So for each coset, I sum over the elements of that coset, this quantity. But then Q of x is C here. Or for all these x here, Q of x is C. So I get chi of C. Chi is, I mean, chi of Q of x is just chi of C bar that comes outside. And I get the sum remaining is f of x summed over the coset, which is my, by definition, small f of C. So this is small f of C. So this is chi of C. So that comes out here. And this whole thing I am calling f of C, small f of C, and that's what I have. So this is actually up to the scaling is small f hat of chi. Does that explain?
Yes. Yes.
Was it this line that? Huh?
Should M be the size of G mod H or H?
Okay. You are right. That's a good point. So this is actually size of G mod H. Yeah. So right. Okay. So if I use the G mod, yeah. So sorry, this was wrong. Here I should have got what? Actually, I should have got the size of square root of size of G mod H, which is n over m. Okay, so it is square root of n over m which comes here, which is okay. So it looks like, sorry, thank you for this correction. Otherwise, this mistake would propagate further. 1 by square root m, small f hat of, okay. Yeah. So this is what we have. So what is Poisson? So now is it okay? Any questions so far? Okay, so now I want to state the Poisson summation formula, which is, well, it's almost here. So, yeah, 1 second. So, what did I do? 1 second. Hold on, sorry, I went to some other window. Yeah. So, what is Poisson summation formula? Okay, rather, let me just now write. Let's consider sum over x in h f of x. Okay. So what is this? This is summing over a coset, right? I mean, h is a coset itself. This is actually small f at identity of G mod h. The identity coset in G mod h is the one that corresponds to the h itself, right? So that is f at 1. But by the Fourier expansion, so this is over summing over all characters of G mod h. We can sum over all characters of G mod h. This is the Fourier expansion of f. F hat of chi times chi over square root of that, which is, what is the square root of the size of G mod h? So this is just Fourier expansion. It is okay. I'm writing the function, chi at evaluated at the identity of G mod h. Okay. But what is the character evaluated at identity? It's just 1, right? Any character is a homomorphism. It takes identity to 1. This is just 1. So we get square root of m over square root of n times sum over all chi in G mod h of small f hat of chi, and this is 1. But now I bring this relationship that we found. Small f hat, I want to write everything back in capital F terms. So this is just capital F hat at chi compose q times what? Square root m. So, oh, did I make a mistake? Is this correct or did I make a mistake here? Is 1 by root of that size, so that is okay. So then I get this to be m over. It looks a little weird to me. I wonder if I made a mistake or not. Did I make a mistake anywhere? It seems okay. So then this is square root m times that. So I get m over square root n. Looks okay. Maybe that is the right one. Okay, I am not too sure. There will be a constant here. I thought it was something. Okay, it looks a little asymmetric looking, but maybe it's because I'm thinking wrong. Okay. No, this is okay. So we can write. So consequently, we get the Poisson summation formula. This is the Poisson summation formula.
Is it better to divide both sides by root m? Then maybe it doesn't look so bad.
Exactly. So that's what I'm going to do. That looks a bit nicer because this side is over h, which has size m, and we are dividing by square root of m, right? So f of x. So here we are summing the function, okay, on the group elements, and it is same as 1 over square root of n over m, which is the size of the G mod h or its dual. They are the same size. G mod h dual of f hat of chi compose q. Okay. So this is the Poisson summation formula, right? So as written, maybe it may not convey much. It's a amazing formula. Yeah. Any
So
questions?
Manju, I think that n by m in the right hand side, shouldn't it? You're dividing by square root m, right? So it should just be.
So
Okay. Yeah. Okay. Correct. Okay.
So I have just written it as 1 by the square root of the size. It's okay, right?
Yeah.
Sorry, one very silly question perhaps.
Go ahead.
So here Q is unspecified. So does that mean for all Q?
Sorry, say it again. I didn't catch it. 1 second.
In this formula, Q is unspecified.
Which one? Q.
In the Poisson
Q,
summation formula, in the final line. we don't explicitly say anything
Oh,
about
no.
Q.
Q is the quotient from G to G mod H. So throughout, Q is the quotient map from G to G mod H. That's how I get the character of G from character of G mod H by composing with this. Maybe I will let me work out one example. Okay, so to say what it looks like, as I said, I could not find an exact application of the formula in this form. Okay, so in ordinary Fourier analysis, what will come out is, I'll just say in an impressionistic way, there will be 2 pi's hanging around, but there will be a formula like this, that you can sum a function on integers and it is the same as the sum of the Fourier transform at the integers. Okay, oh sorry, this is all capital F. This is how Poisson summation formula looks in the continuum setting, which some of you may have seen. So this is an analogous thing. The sum of the function on certain set is sum of the Fourier transform on a certain other set. So going to this type of abstraction somehow separates out the Z here and the Z here. I mean, so it's somehow a bit, one has to be cautious. What is this Z and this Z? One side is a group and the other side is the dual of the quotient group.
Yeah, maybe we can just do the Zn example and check whether.
Right. So Zn will be a good example. So that's the example that I want to give. So let's write n as p times q. I don't mean that they are prime numbers or anything like that. So and g be Zn. Okay. So now let's take h to be. So this is 0, 1. That's how we write n minus 1. Addition modulo n. Let's take the subgroup to be with multiples of p. All those multiples of p, which is just 0, p, 2p up to q minus 1p. Okay, and g mod h can be identified as, I mean, g mod h. What is g mod h? Basically, this is one element. So each residue modulo h. So g mod h is just 0, 1 up to q minus 1. Okay. What is the quotient map? Quotient map is just the residue modulo p. Okay, so q from g to g mod h is q of x is x modulo p. So when you take, sorry, did I do it wrong? Sorry, this is p minus 1, not q minus 1. G mod h will be 0 up to p minus 1. So you take any x here and map it to h mod. So in other words, 0, 1 up to p minus 1 will get mapped. 0 will get mapped to 0, 1 will get mapped to 1, p minus 1 will get mapped to p minus 1. Again, p will get mapped to 0, and p plus 1 will get mapped to 1, and so on up to 2p minus 1, and so on. Then 2p will get mapped to 0, 2p plus 1 will get mapped to 1, and so on. Okay, so modular arithmetic, that's all. So these are the, so this one is one coset, namely h itself. This is the other coset, and so on. Okay, so what is the formula that is telling us? So what are the characters of this? G mod h dual, we know. G mod h dual is just, what are they? I mean, so they are these complex exponentials, right? So G mod h dual we can write as, let's write it as chi 0, chi 1 up to chi p minus 1, where chi k of j is e to the 2 pi I j k over p. So this is modulo, this is isomorphic to z mod p. So this is the so for 0 less than equal to j less than equal to p minus 1. So this is the, these are the characters, phi k of j. So what is the Fourier expansion telling us? So if f is, then if f is a function from Zn to complex numbers, if we sum it over h, so we take what is the size of h, h is size q, m is now, so n is small n, m is the size of h, which is q. So 1 by root q times sum of f of the multiples k times p. So I sum the function on the group, that is this side. What I have written is this side. Now let's write this side is equal to 1 by square root of n over m. N over m is p. It will be 1 by root p. Sum of f hat evaluated at these ones. Chi k compose q. Meaning, what is chi k compose q? Chi k compose q is, so this is from this here, j is in Zn, right? So chi k compose q should be a character on G. So chi k q I want to evaluate at J. What is it? Well, it is e to the 2 pi I k times q of j over n, right? So by definition, q of j, that is instead of j I have q of j. But what is q of j? Q of j is j mod n, j mod p. So I can write this as e to the 2 pi I k j over, sorry, this was p. Sorry. This is, let me repeat, chi k is given by this. Chi k compose q of j is 2 pi I k q of j over p. Now, q of j is nothing but j mod p. So I'm saying that this can be written as kj over n. Why is that? I mean, it's the yeah. Is that right? So if j is of the form p times b plus r, oh, sorry, no. No. Sorry, it is not j over n. It is jq over n. It is jq over n. Right. Sorry. This is jq over n. If I put jq over n, what will it give me? pqd, which is nd. It is just d plus jq over n will be r over p. And what I wanted is r over p, right? That's what I wanted here. So this is actually the same, because anyway e to the 2 pi id will be 1. So this is like this. So in other words, it is the kqth character of z mod n. That's why I wrote it like this. You can write q with the k. It is e to the 2 pi I kq. Kq you think of as L times j over n. So what I have here is f hat of kq, and I have to sum k from 0 to p minus 1. Okay, so you remember that in Z mod n, I don't write f hat of character, but I simplify and write f hat of a number. So this is actually the same. So this looks very symmetric. Are there any questions here? I mean, maybe going over it oneself is the easiest way to see. But I can explain again if something was confusing. So this is the relationship. That it's a funny thing. I mean, what if you are summing over multiples of p, f hat you are summing over multiples of q, and up to this constant scaling, it is the same, whatever function you put. So by putting different functions, you get certain identities. And these identities need not be obvious actually. So there's much one gets out of that. Okay. Any questions here? Okay. If not, then I will proceed. So this is the Poisson summation formula. I would like to definitely find an application for it in this form and give you, but I don't know. I have to look up. Okay. But if not, then I move to another topic. No. So these are three things. So remember, so what we have proved about general Fourier analysis is, so we have G finite abelian group. So three things. So of course we have the full Fourier transform. Fourier transform is well defined for functions in L2 of G. We have defined that, and we have Plancherel. We have Fourier inversion, which is closely related to the duality that G hat is actually G. And now we have the Poisson summation. So these three things are the most useful things actually. I mean, so one gets a lot out of this by applying these. So in some sense, so there is somewhere I had read, I don't remember the exact quotation. Athiya, probably it was Michael Athiya who said, see, when you want to go deep into a subject like mathematicians do, you don't stop here. I mean, so if you go to one of these Fourier analysis courses, either the representation theory course that Shaunak Dev is doing or harmonic analysis that Thangavel is doing, you go deeper into the Fourier transform, its properties and other things. But what are actually most useful are not necessarily the deepest or the hardest, I shouldn't say deepest, not what is useful is not necessarily the mathematically hardest things. It may be mathematically the most natural and most lying, maybe on sort of on the surface. These things, these are exceedingly useful things. Most of the time, you keep using these again and again. Okay, so that's what I say now. Now I want to go and maybe do one thing. So this is the basic Fourier theory for finite abelian groups. So to speak, I have completed. Let's say. I will come back to what I will do is later I will come back to. So I want to now go into some kinds of uses. Before going to Fourier analysis on the circle or on the real line, I want to do some applications. So just to give you a map of some of the things we want to do. So I want to do Fourier analysis on, we will stick to Z2 to the N and expand a bit. And then there are some applications to what is called social choice. So this is some subject. Okay, so social choice is questions of how one does voting and such things. Okay. So the point is the following. I mean, let me say what is the subject going to be. So a function, see, Z2 to the N is what? It is the all tuples of plus minus ones, right? So, and you have a function on, let's say, Z2 to R. Or let's particularly take function into -1 particularly. Okay. So the interpretation, one has a nice interpretation of such functions as follows. What we think of is Z2 to the N. So the coordinates we think of as voters. There are N voters. There are two candidates. +1 and -1. Each of them, each tuple indicates a voting pattern. This person votes for +1, this person votes for -1, -1, +1, +1. So each X in Z2 to the N is a voting pattern. And what is the function f? F takes all the votes and gives 1 or minus 1. So this is how you make a decision by combining the votes. Okay, so I mean each function gives a decision mechanism how the votes are combined. Okay, so in somewhere you may take f of x to be the majority, meaning if there are more pluses, plus ones, you say f of x is plus 1. If there are more minus ones, you say f of x is minus 1. This is normal voting system. But you can have other things. So f of x can be x1. Everyone can vote, but Modi will decide what will happen. So that is one voting scheme. So there are many other voting schemes that you can do. Okay, so this is what social choice is refers to. So we will see some interesting theorem using Fourier analysis on this. Okay, after that I will go to Fourier analysis on Z mod n. And I will do something, a very interesting theorem called Dirichlet's theorem. On primes in arithmetic progression. It's a stellar theorem. It is called the starting point of analytic number theory. So what it is the following. See, everyone has seen in high school or somewhere that there are infinitely many primes. But now let us look at modulo 3. So modulo 3, a number can be 0, 1 or 2. How many primes have 0 mod 3? Of course, there is only one prime which is 0 mod 3, namely 3 itself. So you can't have too many primes which are 0 mod 3, only one. But are there infinitely many primes which are 1 mod 3? Or 2 mod 3? Okay, are there, in fact, one can ask a final question, are there equally many primes which are 1 mod 3 and 2 mod 3? But one would have to make sense of equally many, because the answer turns out to be yes. And that is what Dirichlet's theorem says. Okay, not just for mod 3, you can take anything. You can take mod 6. So mod 6, you can't have too many primes, 0 mod 6 or 2 mod 6 or 4 mod 6, because those are even numbers. So, but there will be infinitely many primes which are 1 mod 6, 3 mod 6 and 5 mod 6. So that is Dirichlet's theorem on primes.
Seems to be a problem, right? 3 mod 6 cannot
be. Sorry, yes. Okay, so not 3 mod 6. 1 mod 6 and 5 mod 6. Only numbers which are co-prime to 6. Okay. So generally speaking, you have to have co-prime to 6. Otherwise, you won't get, for a trivial reason. But whenever it is, so you take any arithmetic progression, then as long as it doesn't have this trivial obstruction, you will have infinitely many prime numbers in that arithmetic progression. So that is a great theorem of Dirichlet. And unlike Euclid, there are many elementary proofs for saying there are infinitely many primes in arithmetic. There are infinitely many primes. So starting with Euclid, there are many proofs. But this one is not so easy. So this we will use the character theory of Z mod n to prove this. It leads to some interesting concepts of analytic number theory and so on. This will have a little bit of overlap. Some of you may be taking a course. Soumya Das is teaching a number theory course, analytic number theory course. He will be doing, I don't know if he is doing this one, but he is doing many things, including probably this one. Okay, so this is the map of things to come. But before that, I want to also expose you to another general fact in Fourier analysis, this uncertainty principles. So I want to do a bit of that before, and then we will come to these applications. And after that, either I will continue with a couple of more applications in finite level, or I will go to Fourier analysis on circle group and R and so on, and more applications there. Okay. So that's to give a overview of what will come. Okay. Any questions, comments, or anything? Okay. So now let me go to uncertainty principles. So this is also something that. So again, so uncertainty principles. So the first uncertainty principle is due to Heisenberg, which is actually I'm not sure if Hardy proved his before Heisenberg, but anyway, Heisenberg's uncertainty principle. That's where the name comes from, which says that you cannot. I mean, you may have heard that you can't measure the position and the momentum of a particle simultaneously. So that's actually mathematical formulation brings to a statement about Fourier transforms, not discrete one, but everything can be done in discrete setting, and we will actually prove a nice uncertainty principle right now. Okay, so let's do it. Let me not explain. Let me explain later. Okay, what it is going to be. So let's start with G, a finite abelian group. Okay, so n is going to be the size of the group. Let's take G hat is its dual. So I take a function in L2 of G, then f hat is in the L2 of the dual. So let's just write down the definition. I mean, let's just recap the relation. F of x is 1 by root n f hat of chi of x summed over chi in G hat, and f hat of chi is 1 by square root n f of x chi of x conjugate over x in the group. And so this is the relationship. Okay. So one of the things that we observe here, by the way, okay. So maybe if just in case everyone is not aware, so let me recall the LP norms. So if I have a function on a finite set, let me just write it for f, then you will also see what it is. So when I write norm f sub p, okay, so this is just a definition. Norm f sub p is whole raised to the 1 over p. Okay, so this is a norm for 1 less than equal to p less than infinity. There is also an infinity norm. So for p less than 1, this is not a norm. Okay, so these are really norms on Cn if you want. But this is how we write. So the 2 norm is something we have already seen. Fx square to the 1 over 2, that is special. It comes from an inner product. These other norms do not come from inner products because they don't satisfy the parallelogram law. I mean, so I am not, I assume that probably people have seen this. If not, people can interrupt if you want to know something, but that these are norms of 1 less than equal to p less than infinity is a fact. And all those norms are different ways of measuring the size of a function. So 2 norm is the most important, but 1 norm is also intuitively simple. 1 norm is just summation mod f of x. No p is here, mod f of x, you sum. That is a 1 norm. So as p goes to infinity, what happens? So when you take this, when you raise things to a very high power, the slightest differences will get magnified, and only the largest one will start mattering. So this one, as p goes to infinity, this will converge to the maximum of these numbers. And that is called the infinity norm. So we will write LP between 1 and infinity, both 1 and infinity included. So whenever we say norm infinity, you don't write this formula, write this formula. Okay. Is there any anybody who is not at all familiar with these norms, it's a good idea to write these norms in R2. How do these norms, for example, what does the unit ball look like in these norms? So for example, R2 means function on two variables, function on a set of two elements. Function on a set of two elements can be identified with C2. For me, functions are complex valued, but if we take real valued functions, it will be R2. So the unit ball in 2 norm is this. This is the unit ball in 2 norm, but the unit ball in 1 norm is where mod x, so there are two coordinates xy, mod x plus y less than equal to 1. So this is the unit ball in, so this is p equal to 2, this is p equal to 1, and p equal to infinity is the other important case. When p is infinity, you want the maximum of x and y to be less than equal to 1, and that is the p equal to infinity. So it's sort of, if you take any p between 1 and 2, it will interpolate between this and the circle. And so I could have written them in the same picture. These numbers, this is actually, these are the same. So this one is inscribed in this circle, and this circle is inscribed in this square. And in between you will have this one will expand to this circle, and this circle will expand to this square as p goes from 2 to infinity. That's how you understand these LP norms. Okay, any questions or anything about this? Is everyone familiar with it reasonably? In the finite setting, at least. When you go to the infinite setting, we need Lebesgue integration and all that. At that point, I will take stock of what people know and don't know. But finite dimensional setting, it should be familiar. So one observation that we make immediately from here, key observation. What is the time? If you look at this formula, from this formula, I can say that if I take the L infinity norm of f, mod f of x is less than equal to 1 by square root n. I put the absolute values inside. These are absolute value 1. So each of these is f hat of chi, right? So that is the sum of mod f hat of chi. So that is L1 norm of f hat. Okay, I should write here L infinity of g if you want. L infinity of g is bounded by L1 of g hat. So just to say what I said, mod f of x for any x, for all x in g, mod f of x is bounded by 1 by root n summation mod f hat of chi. Since mod chi of x is 1, and that is just the L1 norm of f hat, right? On g hat. So that's how we get. Similarly, from this one, we see that f hat L infinity norm on g hat is bounded by 1 by square root n times, because that's the size of g hat also, f L1 norm of g. Is okay? So you get this, right? I mean, so these are very easy. Now I write one more trivial inequality, and I will say, so so what is the other trivial inequality I want to write? I want to just finish and actually get an theorem which is amazing. So just give me a minute, I will finish this. So, but one thing is L1 norm, there is a simple bound which is 1 by root n. This is the summation of f hat of x, right? Over x in g hat.
It's 1 o'clock.
Oh, okay, it's 1 o'clock. So let me just, okay, maybe I will do it next time. Let me not exceed. So let me continue next time and get this uncertainty principle, which I will explain last time. But already this, okay, I'll explain next time. So let's not overstep time. I'll continue with it. Okay, so I'll stop the recording now. Any questions, comments? I am willing to stay.